Welcome back. This is an Aleks training video on deducing a rate law from initial reaction rate data. So if you do an experiment and you find out how your concentrations are changing and how fast something is happening originally, you have to use that to deduce what the rate law would be. And then you could use the rate law would be very useful later, but you have to figure it out based on just the information from the experiment. So let's look at what we have here. We have hydrogen and iodine being used up to make something. And it gives us the original rate of a reaction. Okay, you can have that. It's to the side, initial reaction when the concentration of hydrogen is 2.39 molar and the concentration of iodine is 1.17 molar. You see what the reaction is. Now look what they've done. In the second term, they've changed the concentration of iodine. They've left hydrogen alone, changed the concentration of iodine, and then tested the rate and found out how fast is it disappearing. Okay, from that, you could figure out, is iodine is it going down the same? Is the rate going down the same as the concentration of iodine? If it is, then iodine is to the first order. It would be to the 1 power. If it's going down, as you half one, if the other one's going down by 4 times, you realize that you've got a square somehow, then it would be to the 2nd power, and that's what we're doing. Okay, so let's look at what I've done in black. In black, I've got the concentration 2.39. Okay, you can see that that's a concentration of the first hydrogen, and then in the third test, we kept the iodine constant and changed the hydrogen. So let's just look at the hydrogen change. From 239 concentration to 0.724 concentration. What is that a difference of? Okay, I just divided it out, and it's a difference of 3.3. Okay, now take the initial rates of each one and see, do they go down by the same amount? So I took the first rate, 3.0 times 10 to the 5, took the second rate, divided it into it. Now, check this out really carefully. Notice that this number looks bigger because it's 9.1, but it's actually a smaller number because it's to a smaller exponent. It's got one less decimal place. So it's 10 times smaller, almost, than the other one is. Okay, it's actually 3.3 times smaller. Okay, so I took 3.3 times 10 to the 5. That was the first concentration. Then divided by 9.04. That's the second concentration. And I also got 3.3. Now, what does that mean? If the concentrations go down by the same amount that the rates go down, then the reaction is in first order in that particular thing. So it's first order in hydrogen. All right, so let's do the same thing with iodine. In iodine, they left in the second test, they left the hydrogen concentration the same, and they reduced the iodine concentration. So I have the original iodine concentration as 1.17, so that's what I have here. And then it went down to 0.344, and that's what I have here. So when I divided that, how much is it dropping? Okay, to what order or what function is it? It's 1.17 divided by 3.44 is 3.4. Okay, now do the same thing for the rates. The original rate was 3.0 times 10 to the 5, that's here. And then the second rate was 8.8 times 10 to the 4, that's here. And when I divide it, it's also the same. Okay, so when I know that the 3.3 doesn't change to 3.3 and the 3.4 doesn't change to 3.4, that means both of these are to the first power. So I can figure out the rate. I know that the rate is equal to some constant, okay, which I could figure out later. And then the first one is to the H2. That's the concentration of the first reactant. And it's to the 1 power. Okay, so I don't actually need a power there, to the 1 power. And then the second one is iodine. And it's also to the 1 power. So I have rate equals constant times the concentration of hydrogen times the concentration of iodine, both to the first power. Now I could figure out, now that I know what the powers are, I can figure out my K. I can simply put in the initial rate and the concentration of one in the next based upon that rate. Okay, so let's see what we got. We know that the initial rate, that first one, it doesn't matter which test you take, was 3.0 times 10 to the 5 molar seconds. Okay, I'm going to get K by itself, so I'm going to divide by the concentration of hydrogen. So the concentration of hydrogen, and this is to the first power, 2.39 to the first power. And then I'm going to do the same thing with iodine to its first power, 1.17. Okay, so do that quickly. 3 times 10 to the 5 divided by 2.39 equals, divided by 1.17 equals, and I get the rate, okay, as 1.072846261. I'll round it in a minute, times 10 to the 5th. Okay, that's one of your questions. That's your rate. You have to be really careful of the units, because the Aleks is going to require that you do units, and this is going to be meters to the -1, seconds to the -1. Okay. It's the way that everything else cancels. If you know that the rate is in meters per second, okay, and the concentration, or molars per second, and the concentrations are in molars, the only way everything would cancel would be that the units be in molars to the -1, seconds to the -1. Okay, so that will go in the bottom. Okay, so I only want to round to 2 significant figures, because you can see that these guys here are all in 2 significant figures. So I want 2 significant figures here. And so that's going to be, the rate is 1.1 times 10 to the 5, and then molars to the -1, seconds to the -1. Okay, and then the rate is just what we wrote down before. The rate is going to be some K, which they've already got written, times the concentration of the hydrogen to the first power times the concentration of the iodine to the first power. So I think you can do this.